we have to check where we have connected the LED based on the pin diagram. For that, the datasheet will help us in which pin they have connected the LED, and then how the LED is interfaced. Is it interfaced inverted or direct way? So here it is inverted. So we have to give 0 voltage to make it to glow. See, we have to set that bit to 0 to make it to glow. We have to understand that what value that I have to give in that pin in order to make the LED to glow. We have to find out that. So from data sheet, we come to know which pin they have connected, and then how the LED is connected. After that, to access this pin, which port register I have to use. If it is a port A bit, this particular pin is associated with port A, bit not means I have to use port A register. Okay, to control that, to give the data to that particular pin. Okay, how to make a particular that particular pin, because it is an output. We are going to output a value to this LED. If that is the case, we have to define the direction of that pin, whether it is an input pin or output pin. When you make it the output pin, only then we can control a LED. If you make it to input pin, it won't operate the LED. It will consider this LED as an input. The voltage which is coming from the LED as input, that is wrong. So for that, they have a dedicated register for each port, data direction register. There we have to go and how to set the direction. So,
Yes.
okay, if it is an output, what is the direction value that I have to give? 0. If it is an input, what is the direction value I have to give? 1. We have to put that in trace here. Once you did all these things, only then this will work.
Got it.
Got it now?
Yes.
What, Amir? Clear?
Yes, answer.
So port A, port B, port C, port E, like that they have. Then this is a promo. Then we have PIR1, PIR2. Right. So they say what is PIR1 will do? What is the content of this particular register? It is also a register like status register. They say they have explained that in the page 150. Let us go and see what they have explained there. It's page 21 right now. Right, 26. In which page they told PIR1 register? In page number 26, but it is not there. Maybe actual page that they mention here is something different. 26. Yeah. Flag bits for peripheral register. This is the PIR1 register, right? It has these, actually each bit in this register is dedicated to reflect the status of some peripheral. That's why they say peripheral register 1. Maybe they have more than one peripheral register. That's why they name this as PIR1. Right. In this, in the bit not, we have timer 1 IF. What is meant by timer 1 IF? If the timer 1 is overflow, if there is a overflow in timer 1, this bit will be set to 1. If there is a overflow in timer 2, this flag will be set to 1. There is a CCP IF. So they have an explanation here. CCP1 interrupt flag, capture mode. So what they mean to say here, if it is 1, a timer 1 register captured occurred. That means a complete capture of input happens, means if there is a complete input capture happened, then this bit will be set to 1 in capture mode, right? If there is no capture done by the timer 1, then this will become 0. In compare mode, a timer 1 register compare match occurred. So it is comparing input signal. If there is a compare match, if it is matching, this bit will be set to 1. If there is no match, this bit will be set to 0. If you want to compare two patterns or to capture a pattern, you can use this. We will study about this later point of time. Right, compare, capture, compare mode. Right. Then we have SSPF, synchronous serial port interrupt flag. If you are using a synchronous serial port related stuff like SPI, I2C, these sort of things, what will happen? The SSP interrupt condition has occurred and must be clear software before returning from the interrupt service routine. The condition that will set this bit are SPI, a transmission or reception has taken place. If there is a valid transmission of bits from the master to slave, actually the SPI, when a master shift a bit to slave, slave will shift a bit to master. There will be a concurrent response. When master gives some command to slave, slave will come up. When the master gives one bit, slave gives one bit. Like that it is. Right. If there is a complete successful transmission happened, SSPIF, serial port, synchronous serial port interrupt flag will set to 1. Right? If you shifted your data, all data successfully from the master to slave, SSP bit will be set to 1. If it is an I2 mode, I2C mode, when you are if it is an your module is an I2C slave, a transmission or reception has taken place. If that is the case, this bit will be set to 1. That means slave has received something or slave has transmitted something. In that time, it will set to 1. If it is an I2C master, because there is master and slaves are defined, they are not multi-master in I2C. Right now, when the master is using synchronous serial port, a transmission or reception has taken place. Initiate the start condition was completed by the SSP module. Initiate stop condition was completed by the SSP module. Initiate a restart condition was completed by the SSP module. Initiated acknowledgement condition was completed by SSP module. Like that, we have many meanings when that particular bit is set, when we are using the module as an I2 master, I2C master, right now. Then TXIF. This is USART feature. This is not an synchronous serial transmission. It is asynchronous serial transmission. Transmission or reception. When you transmit a byte using USART, if there is a successful transmission, the transmit buffer will be empty because they are shifting the bit by bit only. No, when it becomes empty, when the transmitter buffer is empty, which means that we can transmit another byte. So when it is empty, this particular flag will be set to 1. So that in order to check the transmitter buffer is empty or not, we can check this flag. After we put something to transmit buffer, we can validate this bit whether it becomes 1. If it is 1, we can put another word. Do you understand? After putting a word in transmit buffer, we can check this bit continuously. We can poll this bit. If this bit is set to 1, which means that the transmission has happened successfully. We can put in another byte for transmission. As we have a transmission interrupt flag, we also have receive interrupt flag. When there is a full in the receive buffer, if the receive buffer is full, means a complete reception has happened. 8 byte of reception, 8 bit reception has completed. That means 1 byte reception has completed successfully. In that case, your receive interrupt flag will be set to 1, which denotes that the receiver buffer is full. You can read the data now. If the receiver buffer is not full and we try to read a receive buffer register, we will get a junk value because it is not complete. Let's say they are shifting some 1 byte from the transmitter. The receiver has digitized only 4 bits. Right. When we try to read the receive buffer register at that time, we will get junk value only. It is not an appropriate value that was transmitted. So after we initiated the receiver, just you check the RCIF flag if it is full 1 or not. If it is 1, you can conclude that a valid data is received in the receive register, so that we can go and read the data and print the data in the screen. Understood? Come on. Transmitter buffer empty means TXIF will be set to 1. Receive buffer full means receive interrupt flag will be set to 1. If there is a completion in the analog to digital conversion, so you give a physical signal for digitization, the digitization is over, then this flag will be set to 1. If this flag is not there, we will get erroneous result. Let's say I gave a physical signal of 5 volt to analog to digital converter. It is doing a conversion. While it is conversion, it will simply do a lot of accumulation, this, that, and all. When it is doing like that, let us say it has completed only 50% of digitization. If I go and read the digitized result, I will get a wrong result. It won't be appropriate digitized value because conversion is not completed yet. So I have to wait for completion. So to know that whether the completion has happened or not, I need to have some sort of indication. I configured the analog to digital converter. I initiated it. It is doing a conversion. I have also given a physical quantity to digitize. But now I have to know whether the conversion is completed or not. To know that, this particular flag will be helpful. ADIF, analog to digital conversion interrupt flag, which means that the interrupt has been completed. If you enable, there will be a interrupt configuration register that we will study in near future. If you set those interrupt enable bits to 1, what will happen means, if there is a successful transmission, the program counter, that means if the TXIF flag is set to 1, program counter will be loaded with 4. If there is a successful reception of a byte, program counter immediately jump to 04. If there is a complete successful conversion of a physical quantity to digital value, program counter will be loaded with 4. Now let's say all these things are configured. I configured USART, I configured analog to digital converter. Whether successful analog digital conversion happens or the successful reception option, every time program counter will be loaded with 4. Now I have to judge whether program counter is loaded with 4 because of ADIF or RCIF or TXIF, whether it is loaded because of transmitter empty or successful reception or successful analog digital conversion. For that, I told no, they will do that in main interrupt service routine. They will check the flag. main interrupt service routine, because when the program counter is loaded with 4, it will branch to a main interrupt service routine. In the main interrupt routine, they will have different cases. Whether ADIF flag is set. If that is set, they have to run ADC interrupt service routine. If RCIF flag is set, they have to run reception ready interrupt service routine. If transmission TXIF flag is set, they have to execute transmitter empty interrupt service routine. There should be, we have to make some distinction between these interrupts, because for every interrupts we come to memory location 004, which is the same memory location for all interrupts. Got it now? So to make those distinction, these bits helps us. As these bits are set to 1, we can inspect them in the main interrupt service routine and can make a necessary decision which interrupt service routine that we have to execute. Make sense? Understood?
Yeah.